Hey everybody, this is Mr. Beckstrom, and today we're going to be taking a look at section 5.2. This is on definite integrals. So last section we looked at Riemann sum, and we saw that if we take some area under a curve between the curve and the x-axis, we could divide it up into equal size, equal width rectangles and get an approximation based off of either a left Riemann sum, a right Riemann sum, or a midpoint Riemann sum. So now we're really kind of moving this definition here, and we're going to define what a definite integral is. So a function f defined on some interval a to b is integrable on a to b if the limit as delta approaches 0, basically the change in x, of k to 1 to n is basically equal to the length times the height, or the width times the height, and adding up all of those. This is the summation symbol, and summing up all the areas of those rectangles exists and is unique over all partitions. So we get this crazy looking thing that looks like this. So basically what we're doing is we just keep decreasing the width of the rectangles until we just have a whole lot of rectangles in this interval from A to B. And then we're going to take all those areas of those rectangles, and the more rectangles that we get, the closer that the actual area is going to be. And we have a bunch of properties of definite integrals. So, for example, if we go from A to A, so for example, if we just started at A and ended at A, notice that the width of our rectangles would be 0. And if you have a rectangle with a width of 0, then the area is also going to be 0. So the area under the curve is going to be 0. We have a property that if you reverse the limits, so instead of going from A to B, we go from B to A, it just changes the sign of our original integral. So if the original integral is 60, from going from A to B, then going from B to A would be negative 60, and vice versa. You can also, the addition rule here, or the sum rule, you can break them up into separate integrals. And there's quite a few things. So read through these, look at the examples in the book and the homework, and make sure that you can kind of get familiar with these. And I'm going to go ahead and go over some examples. So the first one I want to take a look at here, we'll use some properties, is this one. This is from the book. It's number 51. And it says, use the fact that the integral from 0 to 4 of this function, 3x times 4 minus x dx, remember we always have to have a dx or a d, some variable with whatever variable we're differentiating with respect to, and that the net area under this curve is equal to 32. And let me jump back for a quick and talk a little bit about net area. So for example, on this function here, it looks like it's probably a piecewise function. Notice that anything above the x-axis is green and anything below the x-axis is red. So what happens is when we take the definite integral and we add up all these areas, we're actually, anything below the x-axis, we're actually subtracting that area from our total. So this area here, you have some positive area, you have some negative area, and you have some more positive area. So it is possible, even with something like this, if the area above the x-axis is equal to the area below the x-axis, then that definite integral will actually equal 0 because it'll cancel each other out. Now in this case, it looks like there's more area above the x-axis than below it. So I would suspect if we were taking the definite integral of this function here, that we would get a positive number because there's more area above. If there was more area below, I would expect to get a negative number. All right, going back to this right here. make that a little bit bigger. It says use the fact that the integral going from 0 to 4. I'll try to get both my areas in here. Let's see if I can do it like this. There we go. That should get everything. That this integral here is equal to 32, and the definitions and properties of integrals. So we're going to use these properties and definitions here in order to evaluate these ones down here, if possible. All right. So the first one here says, I want to know from, this is A, instead of going from 4 to 0, this one is going from, it's also going from 4 to 0. And this one is going from, I'm sorry, instead of going from 0 to 4, this one is going from 4 to 0. But it's the same thing inside here. So if we look at our rules there, I can't write today, minus x dx. We see if everything inside is the same, but we just switch our limits of integration here. That's number 2 here, going from b to a to b. You just take the opposite sign of whatever the area is. So instead of being 32, this is going to be equal to negative 32. This is going to be equal to negative 32. All right, let's take a look at b. So b goes from 0 to 4. So it's the same as this one here. And but this one is x, and then x minus 4. X minus 4 dx. All right. So with this one here, let's see, there's no 3 in there. And instead of 4 minus x, it's x minus 4. So what I'm going to do with this one is I'm going to start with the one that I know up there. Oops, that's right there, right? I'm going to start with this one here. And I'm going to try to work my way to this one here. So I know that this is from the top up here, 3x 4 minus x dx. I know that this is equal to 32. Okay. So I'm going to work with that, and I'm going to try to go from here to here and see what happens with my answer. So in order to get this x by itself, I can pull out a 3 because it's a constant. So let's pull out a 3. So, and then we'll have 0 to 4, 3x, 4 minus x dx. And this is still equal to 32. But the one that I have here is x minus 4. So how do I go from 4 minus x to x minus 4? Oh, did I leave that 3 in there? I left that 3 in there by mistake. I can just multiply through by a negative. I can just multiply through by a negative, or I can factor out a negative. So if I factor out a negative 1, I can pull it right out front. So negative 3 going from 0 to 4 of x, and that's going to switch inside here to x minus 4 dx is equal to 32. So now everything here, except for the negative 3, is the same as everything here. And the last thing I'm going to remember, this negative 32 is just multiplying this integral here. So if I just divide both sides by a negative 3, I'm going to get that this function here is equal to this, negative 32 over 3. And there is your answer. And just going back to this right here, I mean, think about it this way. I'll do this off to the side. 4 minus x. If I multiply through by x, multiply through by a negative, that becomes negative 4 plus x, which is the same thing as x minus 4. That's what I did there. And then I just pulled that negative out front. All right, let's take a look at C here. C says this is going from 4 to 0. of this function right here. Let me give myself a little bit more room. Oops. Okay. All right. So usually I pause the video for this. I'll give you a little behind the scenes action. All right. So how do I do this? Well, kind of running out of room. But once again, I know that 0 to 4 of 3x times 4 minus x dx is equal to 32. Let me just check that. 0 to 4, 3x, going back to this one up here, 0 to 4, 3x, 4 minus x is equal to, so that's what they tell me. And I'm trying to get to this right here. So if I multiply, or if I change this, that's going to make that a negative 32. So let's do that first. So I'm going to switch my limits of integration and go from 4 to 0, which I already know is going to dx, and that's going to become a negative 32. And then I want to get this to go from a 3 to a 6, so I can multiply by 2, which then I can bring the 2 inside and make that a 6. So multiply both sides by 2. And I'm going to get 4, 0. This becomes a 6x, 4 minus x dx. And since I multiplied this side by 2 and just brought the 2 in there to turn that 3 into a 6, I have to multiply this side by 2 as well, and that becomes negative 64. Okay, and this last one here, from 0 to 8, well, if I go over here, it doesn't look like there's any rules that will allow me to double one side of the integrand or the limits or to add anything. So there's no way I can use these properties here in order to say what this is. Now, we will be able to say what this is when we look at the fundamental theorem of calculus next session, but you'll just have to wait on pins and needles. All right, so let's go ahead and take a look at one more example here. All right, so this is 59 through 66 in the back of section 5.3, excuse me, 5.2. This one says the figure shows the areas of regions bounded by the graph of f and the x-axis. Evaluate the following integrals. All right, so the first one here, if you want to try this, pause it, and then when you're ready, unpause, and we will go through the solution. All right, so it looks like we have an area of 16 that's above the x-axis between 0 and a. We have an area of 5 that's below the x-axis from a to b, and we have an area of 11 above the x-axis from b to c. All right, so the first one says, what is the integral? That means the net area from 0 to a. So all of that from 0 to a is above the x-axis, and that's just going to be equal to 16. Nice and easy. The second one says from 0 to b. So I have to include the area above, and then I have to subtract out the area below. So in this case, it's going to be 16 minus 5. That gives us a net area of 11. Now, if they were, we have to make a distinction between net area and total area. So net area is where you add in the amounts that are above the x-axis and you subtract out the amounts that are below the x-axis. If you wanted to find the total area, then you have to find where it crosses over the x-axis. So you'd have to evaluate this in two separate integrals, from 0 to a and get a positive 16, and then from a to b and get a positive 5, and you can say there's a total area of 21. So remember, the integral, the definite integral, just shows the net area. All right. How about from A to C? So this is going to be equal to 16. Oh, I'm sorry. From A to C. So this is going to be negative 5, because we have to subtract that area out, plus 11. So that's going to be equal to a positive 6. It's positive because there's more area above the x-axis than below the x-axis going from A to C. All right, how about from 0 to C? That's what I was trying to do before. So we start with 16 minus 5 plus 11. So that's going to be 11 plus 11 is 22. It's going to give us an area of 22 here. Now this says the absolute value of the function from 0 to C. Way to ask for the total area there. So we're just going to take the positive values from each one of these areas here. That's going to be equal to 16 plus 11, going too fast, plus 5 plus 11, and that's going to give us a 32, I believe. All right, next one here says from 0 to C, so from here to here, and we want to do 2 times the absolute value plus 3 times just the normal values. All right, so that should be, so this one should be 2 times, and we already know from 0 to C of the absolute value of f of x, that's 32, and then plus 3 times, and this is going to be the net value from 0 to C, which we calculated up here, which is 22. And this should give us a total of, let's pull the calculator out here, 2 times 32 plus 3 times 22. And that is going to give us 130. This should be 130 right there. All right, next one says from A to 0 of our function. Well, we already know from 0 to A is 16, so from A to 0, we just flip the limits there. You're going to get a negative. That's just going to equal a negative 16. And the last one is from C to 0 and the absolute value. Well, we know if from 0 to C of the absolute value is 32, so then this one here would be negative 32. Oh, wait, yep. All right. I hope this helped today. If you have any questions, please let me know, and I hope you all have a great rest of your week. Thanks.